Okay, let's try it again. Here's tape number 2 on what I promised I owed you anyway. What was it? Range. Okay. So remember, range means Y values. Okay, so this is number 3 in our list, but I skipped it. All right, so let's go down here and look at these two graphs. And again, you are going to have to go to your graphing calculator a lot tonight, but then just answer questions from that analysis. So just do your due diligence. That's what I'll expect from a test. Hold on. Yes. Oh, sorry. Okay, so little interruption from students from last year, trying to claim I'm doing stuff. But anyway, um, so you take this and maybe graph it, but no. Actually, I analyzed this first one a little bit mathematically as well down here. Let's think about it. We can plug in 4, right? And I actually have this down here, this explanation. So I'm allowed to plug in 4 for x. 4 minus 4, 0. So 5 plus 0 is 5. So I know I will get a y value of 5. Then what other values can I plug in? I can't plug in 5, 6, 7, 8 for x because those give me square root of negatives. So I can plug in -3, -2, -1. Imagine I plugged in a negative billion. 4 minus a negative billion, the square root of a big number that's positive plus 5 is a big number. So basically what I'm associating here is, this can get infinitely large. Hold on. Mr. Popular here today. Hold on. Another student interruption. Anyway, um, so or if you can't do that, like what happens when I plug in? Look at this graph. So you put this in the Y1 screen, graph it, and then this is the square root picture that looks like this. So remember, domain is what are the x's? Those are the x's that exist for this graph. All right, and then that domain was already told. I said you could plug in 4 or less. But then the range is the same analysis. These are the y's that exist. These y's forever. So you're going to need to do that. You're going to say, okay, this graph does this, so the range is all these y values. So what is that? And then you have to know that it does start at 5 and goes infinitely up to infinity. So the range is 5 to infinity. This one is much more of a challenge. Hopefully I didn't make a mistake, just making sure. Yes. This one's much more of a challenge. This is that classic rational function. And this is what I promised about. Remember, I was going to show you a little bit about asymptotes that you need to know. The first thing you need to know is vertical asymptotes come from zeros in the denominator because the denominator cannot equal 0. So therefore, I would have a vertical asymptote at x equals 2 and -2. We did this last year. So that would affect the domain. The domain is everything but 2 and -2, and then in addition to the graph behaving. What kind of discontinuities are these? Good answer. They are infinite discontinuities. And then the other thing is, well, what is the horizontal asymptote if it exists? Well, I'm going to go through a little diatribe here. No, that's a negative rant. I'm going to go through a little explanation about what the horizontal asymptotes would be. And I was going to put real general things here, like what if I had x squared over x cubed, ... There's more stuff than that, but these are the high top dog degrees. When the numerator's degree is smaller than the denominator's degree, then the end behavior of the graph behaves to y equals 0. So the graph would approach the x-axis on both ends. That's what y equals 0 is. Then, if you had, I'm going to put some fancy numbers here, 2x cubed over 3x cubed, and these are the top dog degrees of the numerator and denominator. These are equal. When that was the case, then the horizontal end behavior was y equals 2/3. All right? And I'm not going to go into it any further. Hopefully at this point you remember these things. And then what happens if I had a higher degree in the numerator? Then you did not have a horizontal asymptote. You had what was called an oblique or slant asymptote. And we'll talk about that later when they actually come into play. So what do we have here? We have an x squared over an x squared. 1x squared over -1x squared. So the horizontal asymptote is y equals -1. And then, okay, so now I go plot this in the calculator, and you really need to have this stuff in your head before you plot it or put it in Y1 and then look at it, because then it all makes sense. Oh, vertical asymptotes, horizontal asymptotes. Okay, got it. So what's the range after all this rigmarole that I just went through? Well, the range is what y values are covered. Here's this y coordinate. Here's this y. These are 2 time and y coordinates. That just means the function's not 1-to-1. So all these y's exist all the way up to this imaginary dotted line. Remember, asymptotes, for the most part, horizontal ones are approached but not crossed. So the range is negative infinity all the way up to -1. And then only in real special cases are horizontal asymptotes crossed and approached from the other side. This one is not one of those cases. So it is a parenthesis. This could never actually get to -1 as a y value. Union that, what? Well, you union that with, wait a minute, these y values exist as well. And I have them colored in yellow or highlighted, all the way up to this y value. So there's a little gap in the y values in between these two things. So how do I find that point right there? Well, guess what? That is a minimum. Very good. So 84 is, remember, hit the minimum in the calculate feature. Left bound, right bound, guess. Inspires, it's a little bit more specific. And I think on the last, no, you don't care about that. This is 0,0.75 when you do that on your calculator. I think on the previous video that got lost, I actually did that on the calculator and showed it. So anyway, with that being the case, this is a y value of 0.75, and it is on the graph. That's 3/4. So for 0.75, I put a bracket on there because it's identifying that as an existing y coordinate off to infinity. So when I ask what's the range, what are the y values of this graph? And you have to use a graphing calculator in order to do that. Okay, so if I give you a picture, you should be able to figure out what the range is with given points. If you have an equation, you have to go to your calculator and access those points, but also have a little bit of knowledge of asymptotes, especially the horizontal. And then, even odd. Let me take a break for a second. Okay, I'm back. For you, that was a millisecond. For me, it was a few. Symmetry. Okay, this is kind of a pain, and it's a vocab you're going to have to really remember. We used this term last year, so it's not new, but it might be tough that you remember this. So, symmetry. You can do all this reading. I'll put this online shortly here. I think it already is online. And then read. But symmetry is two things. You could either have a function that's even. Even is symmetry with respect to the y-axis. Okay? So a parabola that's vertex is at 0, 0. That is an even function. But really what's true is this little algebra. How do you algebraically approach an even function? What's true is if you plugged in -x for x in the function, there would be no change. You'd end up with the original. And I will show that with number 50. So one way you can maybe detect if it's even is it's symmetric with the y-axis. Another way is mathematically g of x equals blah. And then the algebraic test, if you're even and odd, is you plug in a -x for x and then evaluate, or simplify is a better word. A -x for x goes in like this, parentheses, squared. And what's a -x times a -x? Back to a positive x. So when I took g of x and plugged in a -x, I got the same exact thing I started with. So therefore, that makes the function even. And we can look at that at the charts. See, look, I plug in 1, I get 1 in x squared, the basic even function. I plug in -1, and I also get 1. So when I plug in 1 and -1, I get the same y values. When I plug in 3, I get 9. I plug in -3, I also get 9. There's no change when I do that. This is the symmetry with the y-axis. Hence, the negative x for x check. It's all intertwined, so on and so forth. So what's the other type of function? This isn't even a function. I don't even know why they write this down here. Symmetry with respect to the x-axis is a no-good two-time and non-function. All right, so there's not even a name for that. Just be aware of that. But there is one for odd functions. And what odd functions are functions that are symmetric with respect to the origin. Here's the classic x to the third. Here's a point. That is symmetry. A mirror image over the origin. Those 2 points that point has a symmetric brother or sister across the origin. So that is a demonstration of origin symmetry. So that is an odd function. The algebraic test is the same test as an even test, but the result is different. When you plug in a negative x for x, what you end up with is the exact opposite function that you started with. So that's the algebraic test. So how do I check that this boring x to the third, which is the classic example of an odd function, is odd? Well, when I plug in negative x for x, I plug in a negative x for x and I cube it. What's negative x times negative x times negative x? Negative x cubed. And what did I end up with? Something that's completely opposite, exactly opposite from the original. So when I do that algebraically, that is the proof that this function is odd. Okay, now here's one that is a neither, just for purposes of looking at examples. X cubed plus 0.04 x squared plus 3. And I know what you're probably saying. Oh, whenever I have even powers, it's even. Whenever I have odd powers, it's odd, and that's it. But you're wrong, because there's more cases of either, and it doesn't necessarily have to come from just polynomials. But it is kind of where the name comes from. So there is some sort of something with that idea. So let's look at this. Let's test algebraically, is this even or odd? I plug in a negative x for x. What's a negative x times a negative x times a negative x? Boom. But what's a negative x times a negative x? Uh-oh. So is this the same as the original completely? No, this is jacked up. Is this the opposite of the original? Well, this looks like it's opposite, but these two are not. So this is neither the same nor completely the opposite of. So this is neither even or odd. That's the algebraic test. And if you were to look at this picture, it would be something like this. It's the classic end behavior, positive x cubed. There's no way I could cut this up to have odd symmetry or even symmetry with respect to the y-axis or origin anyway. So it's all intertwined. It all is related. So hopefully that helps.